Hi everyone. In this project, my goal was to build a classifier for the bank marketing dataset that maximized the ROC AUC score on the cargo leaderboard while ensure that the model generalized well to unseen data. My approach focused on two main aspects. First, improving the predictive performance of the model through feature engineering and model selection. Second, carefully evaluate and improve the model fit using validation techniques such as cross-validation, early stopping, and learning curves. To answer the first question, what did I do to improve the performance of the regressor? First, I started with a baseline approach and gradually improved the models through several steps. One of the first improvement was how category variables was handled. Dataset contain many category features such as job, education, contact method, and months instead of using the ordinal encoding, which can create artificial ordering between categories. I use one-hot encoding through a column transformer. This allowed the model to treat each category independently and typically improve performance for tree-based model. Next, I perform feature engineering to extract more useful information from the original variables. For example, I apply log transformation to scroll the numerical variables such as balance, campaign, and previous contact. This transformation help reduce skewness and make patterns easier for the model to learn. I also create several additional features. For instance, I generated a binary feature indicating whether a client has been contacted before. Yes. And I derived new time-related variables such as the numerical months and the quarter of the year. This additional feature helped the model capture behavior pattern in marketing campaigns. For the model itself, I choose XG boosting, a gradient boosting model, are particularly efficient to structure tabular datasets because they can capture complex nonlinear relationship and interaction between variables. Compared with simpler models such as logistic regression, XG boosting is able to model higher order feature interaction automatically through the decision tree. I also tuned several hyperparameters, including tree depth, learn rates, subsampling ratio, and regression parameters. Using smaller learning rates combined with a larger number of boosting rows allows the model to learn more gradually and improve overall performance. Finally, to further improve prediction accuracy, I use model blending. I train multiple XG boosting models with slightly different parameters configuration and combine the prediction using weighted averaging. Since every score captures slightly different aspect of the data, blending them helps reduce variance and often produce a better ROC AUC score. To answer the second question, what did I do to access or improve the fit regression? To evaluate how well the model fits data, I use several validation techniques. First, I apply a stratified k-fold crossing validation. Stratified ensures that each fold maintains the same class distribution as the original dataset, which is important because the target variable is somewhat imbalanced. Cross-validation provides a more reliable estimate of the model performance than a single training team split. Across of the five very consistent, with the average around 0.799 and a relatively small standard deviation. This indicates the model was stable and not overly sensitive to spectral data split. Second, I use early stopping during training. Instead of specifying a fixed number of boosting runs, I monitor the validation AUC during the training and stop the training process when the performance stopped improving. This helped identify the optimal number of boosting runs and prevent the model from overfitting. In addition, I use a holdout validation set to confirm the model's performance outside cross-validation framework. The validation AUC was slightly higher than the cross-validation average, which suggests that the model has sufficient capacity and not underfitting. I also analyzed the learning curve of the model, plotting training and validation performance as the training set increase. I could evaluate the bias variance trade-off. The learning curve show that both training and validation AUC improves as more data were used. As the gap between them remain relatively small, this indicates the model achieved a good balance between bias and variance. Finally, I plot the LC curve for the validation set to visualize inspect to classify your ability to distinguish between positive and negative cases. The LC curve confirmed that the model has strong discriminatory power across different classifier thresholds. Thank you.